Still says going live. It says I'm live. Excellent. Okay. So, you had a major due for me today. I have not looked at any of them yet because obviously here I am with them being due at 7. But I just took a quick peek and saw the people who had turned it in. Thank you for that. Obviously, if there's an issue with submitting something, you can email me. Now, just quick thought. I haven't checked my email at all today. I literally got in, 6:50? Well, I got into the building at 6:50. I got into my room at 6:55. And then I was I tried to boil water and go make copies. And now here I am. So I haven't had a chance to check my email yet, but I will. So here's what I want to do first. I want to watch a quick YouTube video. Now, for those who are going to be online, just so they don't have to watch a screen of a screen, I am going to post the link to that YouTube video. I just have to get the link right now into the chat so that they can watch it separately from whatever this is, just because I think it's silly to watch a screen of a screen. I don't know why I haven't done this in the past. See if I can post this into the chat. There it is. It worked. Good morning. People are saying good morning to me, like polite people. Okay, no. No, it's too late. It's too late. You all get -5 stars. Now, this video, I don't know if you guys are familiar with the YouTube channel entitled Numberphile. Anybody know Numberphile? No? You do? Yes, of course you would. Anyway, no, Numberphile is a great YouTube channel. But anyway, it's just basically this guy going around the world and having like long conversations with mathematicians about cool things in math. It's the nerdest channel ever. But I do have one in regards to that story that I shared with you about that village in Europe getting a whole influx of storks. And the reason why that relates to what we are doing, obviously, is because they found a very strong correlation. But of course, as we've talked about over the course of this chapter, correlation does not equal causation. So what I'm going to say is I'm going to play the video in a moment. For those of you in the chat, if you want to watch the video separately, I just posted the link into the chat so that you can watch that separately so you don't have to watch the screen of a screen, obviously. But yeah, I want to start there. So let me flip my screen over. Come on, screen. Here we go. Chapoom, chapoom. And here is a very quick video on Numberphile.
Next topic is one of the most famous stories in statistics. It's also about where babies come from. I know you know where babies come from, but there used to be this tale, that's what I grew up with, that babies come from storks. If a child is asking awkward questions of his or her parents, the parents would say, well, the storks bring the baby in, draped from their bill in a blanket. That's where your baby brother or your baby sister came from.
Have you figured out where that came from? Why storks are associated with babies at all? Or
so there's a theory. It's something to do with storks being a traditional symbol of fertility, a religious symbol of fertility. And another theory is that storks, when they go fishing, they're looking for embryonic life forms in the water. So that is two theories. I don't know. I'm an economist. I'm not a sort of a studier of mythology and ritual. Anyway, to get back to the important stuff, which is the statistics. So, storks deliver babies. This is the old story. Let me try to prove that to you statistically. I've got my paper here. So, and this is just going to be a illustrative plotting. If you imagine two axes, and here, this is babies per year, and here we have the number of storks. And if you just take a bunch of European countries, and I have actually seen the data, what you find is Turkey, if I remember, and this is Poland, and then you might have Germany here, and then you've got a whole bunch down here, a couple there. And it's not the world's best correlation, but it's not the world's worst correlation. There are loads down here with not many babies, not many storks. You've got these big outliers here, you've got nothing here, you've got no places with loads of babies and no storks. You've got no places with loads of storks and no babies, and you can draw a best fit line, and it goes like that. And there is actually an academic paper about 20 years ago with the title Storks Deliver Babies, P equals 0.008. And without going into the technical details, you probably know that according to the conventional standards of statistical significance, that means this relationship is not a coincidence. There is definitely...
Just for the sake of argument, when they say a P of 0.008, we are going to be studying P values a few months into probably about February-ish. We're going to be jumping into some levels of, actually, no, maybe we'll do probability at that point. I don't know, but we're going to be studying hypothesis testing. You'll see when we get there.
Definitely a correlation between storks and babies. Now, you're probably thinking to yourself, okay, so what's the trick? Because, surprise, surprise, storks don't actually deliver babies. Email me if you actually want me to explain where babies do come from.
Will I get a reply?
Well, maybe. So what's going on here? What's going on here is, basically, as I said, I think this is Turkey, this is Poland, there's Monaco, there's Luxembourg, there's Liechtenstein down here, lots and lots of places with very small amounts of land. There are no storks and there are no kids, basically. And here are places that are really big, lots of storks, lots of babies. And that's what's going on. That's enough to drive that statistical correlation. The amount of land is the hidden factor, yes. The secret thing that's driving both a large population, which means a lot of babies, and it is driving the large number of storks. Because bear in mind, I didn't say birth rate. I'm sure I expect there's no correlation for the birth rate. What I'm talking about is the number of babies born each year in these countries, which is very closely correlated to the population.
So you would also perhaps expect a correlation with trees.
Yeah, probably number of trees versus number of babies a year. Trees also deliver babies. I mean, you could go in all kinds of places like this. And there are lots of these spurious correlations out there. Actually, there's a website maintained by a guy called Tyler Vigeland, I think, called Spurious Correlations, full of all kinds of fun stuff like this. But I said at the beginning that this is one of the most famous stories in statistics. It was made famous by a fellow called Darrell Huff. And here, for me, is where this gets really interesting. So Darrell Huff was a journalist. And in 1954, he published a book with the title, How to Lie with Statistics. It got a rave review in the New York Times. It became, many people say, the best-selling book about statistics ever written. And I loved it when I was a teenager, reading about all of these tricks, all of the different ways you could be deceived. He's got the storks and babies in there. It's got loads and loads of great examples. It's got dodgy maps. It's got dodgy graphs. It's got all sorts of great examples. It's a very funny book. I'm not the only person who liked it. Ben Goldacre, who wrote Bad Science and many other great books about numbers, he praised Darrell Huff. Charles Whelan, who wrote a book called Naked Statistics, he said it was an homage to Darrell Huff. There are loads of fans of Darrell Huff out there.
This book is in praise of statistics, though. This book is supposed to be doing a service to statistics, presumably.
So that, I think, is where the important question lies. It is loved by nerds, but it is not really in praise of statistics, because what Darrell Huff is doing is, in chapter after chapter, example after example, he's debunking dodgy statistics. And he just doesn't have a lot of positive examples of statistics being used to illuminate the world. And that's where I start to get a little bit queasy, because that book was published in 1954. And you know what else happened in 1954? Two great statisticians, epidemiologists, Richard Doll and Austin Bradford Hill, provided some of the first solid evidence that smoking cigarettes might well give you lung cancer. Because the same year, two different visions of what you can do with statistics. Darrell Huff is saying, it's a bit of a joke, it's a bit of fun, I'll tell you the story about the storks and the babies, but don't ever take statistics too seriously, because they're just a way for people to lie to you. Austin Bradford Hill and Richard Doll are using this vital tool to find out the answer to one of the key medical questions of the 20th century. And when you think about it, they couldn't have done that in any other way than using the statistical lens. So even to notice that lung cancer cases were on the increase, and they were massively, you need to be systematically counting cases of lung cancer. Maybe there'd be some anecdotes, but you need the numbers, you need the data. And then to show compellingly that there's evidence of causation you really need to work hard with the statistics. So a lot of people at the time thought it was something to do with cars, which is not crazy. You think about it, between the beginning of the 20th century and the 1950s, lung cancer's on the increase, so are cars, loads of cars. Maybe it's something in the tarmac, maybe it's something coming out of the exhaust. It's not a crazy idea, but it turns out it wasn't the cars, it was the cigarettes. This is so important. This is such a key fact. Understanding that this thing is true, this has saved literally tens of millions of lives, possibly hundreds of millions of lives. And you've got Darrell Huff in, remember, the best-selling book ever published about statistics, saying, don't ever take statistics too seriously, because they're basically, liars will use them to lie to you. There's a twist in this story, because in the 1960s, the US Senate held hearings to decide whether cigarette packets should have warning labels on them. Should smokers be warned, maybe this is going to kill you? And they got all these expert witnesses in to discuss the evidence. And one expert witness came in and he told the senators, look, don't worry too much, because there are a lot of funny correlations out there. Let me tell you about storks and babies. And he sat there and he told the senators all about how you could demonstrate this correlation between babies and storks. He used a slightly different example, but the same basic argument. And it's the same with cigarettes and lung cancer. And the senator who was chairing the commission said, do you seriously mean to tell me that there is as casual a relationship between smoking and lung cancer as there is between storks and babies? And the expert witness says, yeah, they seem to me to be about the same. And his name, you may have seen it coming, Darrell Huff, the guy who published How to Lie with Statistics. He was actually working on a sequel which was never published, called How to Lie with Smoking Statistics. So he'd taken this funny, witty skepticism about statistics in this great little book, and he'd soured it into this nasty cynicism that everything out there is fake news. You can't believe a single thing you're told. And he'd then gone to work for the tobacco lobby, who found him to be the perfect witness for their case.
If you'd like more.
So, just to kind of put that into perspective, I think it's this concept that people have been talking about in the past, let's say, 5-10 years or something, where people are like, fake news, fake news, fake news. This has been going on since the 50s and 60s, probably a lot sooner than that. But he didn't explain it in the video, but I just wanted to explain, there's always a reason, to an extent, there's always a reason that you could potentially point to. You can correlate so many different things, and it's just randomly they just so happen to correlate together. But there are certain instances in which you can find a lurking variable, and you can determine what is causing these two variables to be correlated together. And I believe I mentioned it earlier in the year. I can't remember if I did it for whatever, and I'll say it anyway. But basically, in these places, there was a new style of house that was being built with a very particular chimney that storks like to make their nests in because it kept them warmer. So when they built these new houses, these young couples coming together and building these new houses for them to live in during these 1800s and whatnot, the storks would come and be like, chimneys to make our nests. So they would come and make their nest and be like, there's an influx of storks. And then there would be an influx of babies because you had young couples newly married in a new home making babies. Again, don't ask me. But anyway, I just thought that was very interesting. So if you want more number file, they have thousands and thousands of videos. It's really fantastic. It's not just on statistics. They have a lot of other stuff as well. But anyway, if you would, I'm going to need those notebooks out and open. You guys are not going to need those Chromebooks. So I would shut those down. Save your battery. Where is it? No, it's not it. Was that it? No, that's not it either. Maybe it's later on. Yep, I'll find it. Let me flip my screen again. There we go. Now, we just spent a ton of time dealing with linear regression, determining how to find that linear regression, finding out what that R value was, determining the R squared value, things of that nature. It's pretty interesting. Let me find something here. Regression outputs. Wanted to find you a good example. That could work. Yeah, that could work. We'll do something like that then. Okay. Boom. Boom. Ah, come on. You're supposed to be larger. Open up in a new tab. There we go. Okay. Now, sometimes you're going to be faced with, just for the sake of argument, regression outputs, where they're going to throw a ton of stuff at you with just a bunch of information and all of this stuff, with a lot of variables and values that you're not really even going to pay attention to or anything along those lines. But I just wanted to point out something very important to you in regards to these outputs, because this is not a basic output that you're going to see. But you will see a lot of like statistical outputs. And the main thing that you're really trying to pull away from it is, what is the slope? What is the y-intercept? What did the regression analysis output produce as a slope and a y-intercept? And typically speaking, it depends on what your input and your output is, of course. But usually it'll say something like constant. It won't say CONS. It'll usually say something like constant. And you have to recognize that to be your y-intercept. Now, in regards to this MPG versus foreign and things of that nature, they won't have two different things there. They will typically just have one extra line up there, which then that variable would be the coefficient on your slope. So just for the sake of argument, if you ever see a regression output like this, you're going to be looking for coefficient, and you're going to be looking for the variable and the constant to represent your slope and your y-intercept. And we're going to have practice with that as time goes on, of course. Furthermore, you're also going to be looking for either the R or the R squared. You could easily get one from the other. In this case, this one gives you an R squared. Do not use the adjusted R squared. They're going to throw that out there. It's calculated in a slightly different way. You do not have to worry about the adjusted R squared. That is more advanced, probably upper levels of statistical degrees when you get to college. But for now, just worry about the R squared. Oh, how do I get R? Well, you square root it, and then you make it positive or negative based on what the slope is. Because the value of the R, positive or negative, is going to be based on whether or not the slope was positive or negative. Weird stuff. Okay. The lesson that I am entitling this today is called Regression Wisdom. It's literally called Regression Wisdom. Today is the 7th. Fun. Pickups, fun. Okay. Now, a couple things to this. Move that over there. There we go. In order to do a linear regression, you have to have a bunch of ordered pairs. You have a bunch of ordered pairs, x, comma, y. They're all labeled out. And then based on the list of x, comma, y that you have, I've talked about it in the past where you can convert everything into a z-score, which is nice. And I'm going to show you something on my graphing calculator in a few moments, but I want to write this down first. If every ordered pair in a scatter plot were, quote, standardized. And what I mean by standardized, I mean converted into their z-scores. Then the line of best fit would be, now when I say line of best fit, I am referring to the linear model. When I am referring to the line of best fit, I am referring to the equation, the prediction equation. Then the line of best fit would be this. There we go. It would literally be, in this case, some weird y equals mx plus b situation, not with a b anymore, but with this relationship going on. The fact that the z of the y would be equal to r times the z of the x. Meaning if you had an x z-score or an x value to plug in, you could plug it in for z of x, or the z-score of the x, multiply it by r, and it would produce on that line of best fit the z of the y. It's a very unique situation because you may not see a lot of examples like this floating around. You may not see a lot of examples like this floating around, but you may see one or two. Now, what I really wanted to show you, I'm just going to get a ridiculous example in my calculator real quick. You don't have to copy this in my calculator per se. Let me make that a 7, and a 5, and a 3, and a 1, and a 1.5. There we go. I just created a scatter plot in my calculator. Zoom in, zoom in, zoom in. There we go. You don't have to copy the scatter plot down. You don't have to copy any of these values. I just want you to visibly see what I'm about to do with this. First, I just want to look at the scatter plot real quick. Zoom 9 it. Boom. There it is right there. Kind of looking like a Big Dipper. Not exactly. But this looks straight enough. I'm going to run a linear regression here. I have to turn my diagnostics on in order to run that linear regression. linreg. By the way, I keep saying I'm going to show you. Have you guys noticed how I've been able to automatically store the equation into y equals? Did any of you catch how I did that? Okay, watch this very carefully. I'll show it to you. It's a silly trick. It's a silly trick. Clearly, you could copy it into your y equals key just by typing it, but I'm just going to show it to you real quick. When you do linreg, usually they ask for the L1 and the L2, which you already have in there. No big deal. But if you want to store it into your y equals key without having to retype anything, if you hit vars, y vars, which is your y variables, function, and there are all your y variables, and you can tell the calculator where to store it. Hey, calculator, I want you to store it into y1. And if it does that, it'll automatically take that line of best fit and store it into my y equals key, which is nice. It's a silly trick. You don't really have to know how to do that. It's just one of those things. But anyway, let me write something down here on the board just for the sake of argument. And then I'm going to copy a little sketch of something. So this is y equals negative 1.5 x y hat plus 8 with an r of negative 0.949 approximately. I'm not putting that into my notes. I'm just showing this to you as an example and just a little sketch of what this thing looks like. I don't like that. I want to draw that again. No, that was fine. That was whatever. I'll draw it again. I'm just going to sketch a little scatter plot here. That was actually pretty good. I'm not going to lie. I'm very proud of myself. Anyway. But I want to do a little conversion in my calculator. A conversion to be able to get some z-scores. And as a reminder, something that you do have to know off the top of your head, how do you calculate a z-score? Data point minus average divided by standard deviation. Watch this. This is really messed up. I'm going to do that here. I'm going to put my x z-scores in right here. It would basically be data point minus average divided by, this is a silly little thing, standard deviation. Boom. Gets me my z-scores there. There's a point that I'm getting to. And then my y values minus the mean of my y values divided by the standard deviation of my y values. What did I mistype? Oh, I put an extra parenthesis? Oh, that's right. Wait, no, I don't see it. Where'd I put the extra parenthesis? Didn't I do it the exact same way? Let's try it again. Parentheses, L2. No, yeah, L2 minus the mean of L2, close, divided by standard deviation of L2. I typed that in, didn't I? I typed that in exactly the same way, didn't I? Yeah. Let me see something real quick. I have a hunch. No, my hunch did not work out. That's really weird. Okay. For the sake of time and energy, because I don't know why it's saying that, because I literally made up these data points off the top of my head and I typed it in exactly the same way, but it's saying that I have a data type error. Let's see what the mean was real quick. Mean of L2. Yeah. That's all. Okay, so hold on. 3.5 and 2.5. Okay. I can get past you. L2 minus, I already forgot. 3.5 and 2.5. Okay. L2 minus 3.5 divided by 2.5. Ha! I got past it. I don't know what's going on with the calculator there. Whatever. Now, these two lists right here are my z-scores. These are the z of the x values, and these are the z of the y values. And here's the point that I'm getting to. Check this out. L3 and L4. Oh, let me get rid of this real quick. There we go. L3 and L4. I put L3 in for the x's, L4 in for the y's. I converted everything to z-scores. What do you notice about the scatter plot now? What do you notice about the scatter plot now that I've converted everything into z-scores? Does it still look like that stupid Big Dipper? Yeah. It's the exact same scatter plot, except everything has been shifted on the graph. What did you call it in geometry? You call it a translation? When I said geometry, did you get a shiver down your spine? Some of you are like, okay, yeah. But it's the exact same thing. It's really weird. Check this out. Negative 0.949x. I said that the z-score of the y would be equal to r times the z-score of the x. Graph. Oh, that's really messed up. It's literally what I wrote down. I just thought it was kind of cool. And then furthermore, I can run a linreg with L3 and L4. Just for the fun of it, let me store it into y equals. There we go. With L3 and L4, which are the z-scores, look at the slope versus the r value. Again, that's exactly what we wrote down. It's just one of those little magical tricks about statistics that you can kind of do that. Where if you convert everything into z-scores, then your slope basically becomes r, which I think is like the coolest thing ever. But no one else is really like, oh, that's okay, whatever, Mr. Murky. I'm like, I'm sorry, that's the coolest thing ever in my mind. Storks and babies. Anyway, back to this. I'll flip this page over. Do this here. Here we go. Some things about R that you need to know. We literally just did these things to R. R is not affected by adding, subtracting the same value to each data point. R clearly is not affected by adding or subtracting the same value to each data point. I converted all of these ordered pairs into z-scores by taking the data point minus the average dividing by the standard deviation. Clearly, subtracting the average from every single ordered pair, from every x value, or the average of the x values and the average of the y values from the y values, by doing that, it clearly did not change the r value. What else did it not change? Well, check this out. R is not affected by multiplying, dividing. Now I'm going to write this all in capitals. By the same positive number. R is not affected by multiplying, dividing by the same positive number. It's not. Now, by doing it by a negative number, now we have a little bit of an issue. If you multiply, divide by a negative number, there is a little bit of an issue. And let me show you that on my graphing calculator. I want to show you that on my graphing calculator so that you can see exactly what's going on with the R value. The R value is supposed to be, for this example, negative 0.949, approximately. Let me show you something here. All right, get rid of that and that. Let's get rid of these lists here. I'll get rid of my z-scores. Get rid of my z-scores. I'm going to take, I don't know, I'll take L1 and I'll multiply it by, give me a number, single digit number. 6. All right, multiply by, I wrote 9. My bad. Times 6. There we go. Multiply it by 6. Cool. So there's my new L1. There's my brand new L1. All right. Let's just see what happens. I want to see what happens here. I just multiplied everything by L1. So this is going to be L3 and L2. L3 and L2. Now, I multiplied I'm not really going to look at the scatter plot. What I really want to do, I really should go here. L3, L2. Because I changed the x values. I just changed the x values. I just want to see what happens. Look at your R value. Nothing changed. That made me, I was scared for a second. Okay. But the R value did not change. Now, watch what happens when I multiply it by a negative. L1 times negative 6. Watch what happens here. Watch what happens here. I'm multiplying the L1 by negative 6. I'm multiplying the L1 by negative 6. I'm violating what I just wrote down. I am violating what I just wrote down. Oh. What happened to the R value? It became positive, yeah. It changed. See, the R value is affected if you multiply by a negative. Oh, no, you guys can't see it on the live screen or live stream because there's the literal glare is right there. But yeah, that's a positive R now. But check this out. Check this out. Check this out. This is going back to your, wait for it, geometry skills. Going back to geometry skills. Watch this. Give me another negative number. 4, negative 4. Watch this. L2 times negative 4. I multiplied L1 by a negative. I multiplied L2 by a negative. They got both multiplied by negatives. Here's L4, L3, L4. Chapow. Your R value is back to normal. Think about geometry. Think about geometry. Think about an ordered pair in geometry, like right here. Here's the ordered pair, like 3, 2. You were taught stuff in geometry about reflections. Am I wrong? Weren't you taught about reflections? Yeah. Transformations. Where if you multiplied the x value by a negative, the x value, it reflects over here. If you multiply the y value by a negative, it reflects over here. And if you multiply both of them by a negative, don't they reflect down here? Yeah. Didn't you have to do the same thing with polygons, like shapes and lines? Didn't you have to like say like I have to reflect it here, reflect it there? Yeah. Am I really, really like causing you to have PTSD? No? You love geometry? All right, whatever. I don't know who that is. I don't know who many people are. But back to this. Oh, I probably should erase that. Give me a moment. So, if both variables are multiplied, divide. Now, mind you, I'm going to underline both variables. If both variables are multiplied, divided by a negative, I want you to think about the reflection across the origin for like a line or something like that. That's basically what's happening here. R remains the same. Now, again, that doesn't mean the equation, the line of best fit, will remain the same. I did not say that. I am simply talking about the correlation coefficient and what happens to it when these things are applied to these data points. And yes, there are certain things that you have to apply to data points. For example, if I am collecting data on average temperature over the course of a month, and you are also collecting data for average temperature over the course of a month, oh no, you collected it in Celsius, and I collected it in Fahrenheit, like a moron. Oh no, I have to convert my Fahrenheit to your Celsius. Oh, good thing the R value won't change, because that's what really matters in this case. If we're trying to find a correlation over the course of time. No. Anyway, another little piece of information. I vaguely talked about this, but I wanted to talk about it a little bit more. If X and Y are interchanged, they're interchanged or switched, R remains the same. Different things about regression wisdom is what they refer to it as. Let's see. Oh yeah, I got to talk about that. Do you guys know about levers? Not levers, leverage. Do you know about leverage? Anyone in physics right now? Cool. I have no idea whether or not you've gotten to this. Have you gotten to like forces? No? Nothing? Okay, what are you guys learning in physics? That's lame. Anyway, think about, here's the ground, and here's like a large boulder that's in the ground. And here's you. Or me, whatever. Clearly, that boulder is a lot bigger than me, and I'm going to have a tough time trying to lift that boulder or move that boulder. What physics and mathematicians over the course of centuries have figured out that, well, you're not going to be able to just move the boulder by your own force. But if you could create a machine that could distribute the forces over the course of various joints and pulleys and whatnot, you would be able to move that. Or if you had like a long stick, jam that thing in the ground, you might have a better chance of moving that rock if you had that thing in the ground and you were able to leverage the weight. There are different weird things about forces that you can do. There was this like ancient guy, I can't remember his name. I want to say it was Archimedes, but now I got to look it up. But he said something along the lines of, give me a place to stand and I can move the world. Hold on, I got to find that. Give me a place to stand and I can move the world. I don't think that's the exact. There it is. Yes, I got it right. It was Archimedes. 2 gold stars to me. Here's what he said. He said, give me a lever and a place to stand, and I will move the earth. Give me a fulcrum, and I shall move the world. Give me a firm spot on which to stand, and I shall move the earth. That is Archimedes. Archimedes. Do you know the other famous story about Archimedes? Running through the streets naked, shouting Eureka? Some people do. Yeah. That's that guy. Anyway, back to this. Why do I bring up Archimedes and levers? Well, I got to talk about what is known as a leverage point. A leverage point. A leverage point. Talking about a leverage point. Here's an example of a leverage point. Here's a weird scatter plot. You can draw that. You don't have to do it exactly. Just kind of make it in the same general shape. Make it in the same general shape. Here's one additional data point. A leverage point is a data point whose x value is far from x bar. A leverage point is a data point whose x value is far from x bar. I'm a poet who wasn't aware of his circumstances. Now, a leverage point does not always have to be in line with the data. It doesn't have to be. If I were to draw this line of best fit, yes, technically it would be in line with that leverage point. But a leverage point doesn't always have to be there. The leverage point could be down here. The leverage point could be up here. The leverage point could be over here. It doesn't matter as long as it is far from x bar. What is going to be x bar? Well, if I looked at all these data points and I were able to find the average of just the x values, the average might be about right there. This data point is clearly farther away. You can identify a leverage point if it is far from x bar. If you can identify a data point as a leverage point, you could put it into the category of outlier. Well, how far away does it have to be? Well, that's the unfortunate part. It's kind of like if it seems far enough away. It's like, oh, how do I know if the scatter plot is good for linear? Well, does it look straight enough? What does it mean to be straight enough? I don't know. Is it straight enough? It's one of those weird things. A different type of linear outlier is also known as an influential point. An influential point. Let me create a little scatter plot here again. Here's my random scatter plot. That's clearly, that's a pretty good linear thing. Well, what would be an influential point? Well, let's say I put an additional data point down here. That data point's not far from x bar. It's pretty close to x bar. But it is a data point that drastically changes the slope of the model when you run a regression, if I could spell regression today, I'll repeat this sentence, by the way. When you run a regression with and without it. Let me repeat that statement because that's an important statement. As I've said, a good mathematician, if you believe you have an outlier for a scatter plot, then you are to run the regression both with and without it, without that potential outlier, and see what it actually does to the line of best fit. Well, and I underlined the word slope here, so I'm going to read this sentence again. An influential point is a data point that drastically changes the slope of the model when you run a regression with and without it. A leverage point might change the slope. I mean, if it does, then I guess that leverage point is also an influential point. You could be both. But a leverage point doesn't have to change the slope. A leverage point could be in line with the slope and not actually change it. So it would just be a leverage point. But if you have a data point that drastically changes the slope when you run the regression both with and without it, then yeah, perhaps you would identify it as an influential point. If I were to look at the slope of this particular line, without it, it would look like this. That would be the slope of the line if I took out that outlier. But if I put that outlier in, perhaps now my new line would look like this. That drastically changed the slope. That is definitely an influential point. It influences where that line of best fit is actually drawn in a great way. Let's talk about something referred to as, and you probably already know this, but referred to as extrapolation. So, back in the day, we had these things called cassette tapes. There were these plastic little things. I'm sure none of you have no idea what I'm talking about whatsoever. Anyway, don't nod. There are these plastic little things with like ribbon inside of them, and then you would put them in these devices that would play them, and you would hear music. It was magic. It was magical. I know. I mean, you guys probably don't really remember CDs that much. CDs were these discs. No? Whatever. Shut up. Anyway, cassette tapes. Imagine for a moment that you're living in the early 1980s. You're living in the early 1980s. The Walkman has just come out. You guys remember Walkman? Some of you are nodding yes. That's weird. All right. The Walkman's just come out, and you're like, man, cassette tapes are blowing up right now. People are buying music on cassette tapes left and right. They are cheap to produce. The music stores are making tons of money. I got to invest it all in cassette tapes. Man, look at this scatter plot of cassette tape sales. Look, 1981, 1982, 1983, it's just sales are going up and up and up and up and up and up and up. Clearly, man, by 1995, by the year 2000, I'm going to be a billionaire. So you invest all your money in cassette tapes because you thought, well, based on this scatter plot of data, based on the correlation between the years going by and the number of cassette tapes being sold, I was supposed to have a lot of money. But clearly, in the late 80s, early 90s, CDs actually came out. Fun fact, do you guys know how many minutes of music you could fit on a traditional CD when they first came out? No? I don't know the exact number, but the exact number of minutes that you could fit, that you could burn onto a CD was equal to the exact number of minutes of one of Beethoven's symphonies. I thought they made it that way so they could fit the symphony out in there. It's so awesome. Anyway, but my point being, you have all this data and you're like, man, let me look into the future and see what happens. Ooh, looking into the future might be a bad idea. I could also do something like this. Hold on, there it is. Imagine for a moment that I had some weird thing between height and shoe size, right? Height and shoe size. Clearly, can we all agree that the taller you are, more likely you're going to have a larger shoe size? Clearly, yeah, more likely. It's not always the case. It is not always the case. But clearly you're going to be like, yeah, height and shoe size. It's going to be something like this. Cool. Hey, let's figure out the shoe size of someone who's 10 feet tall. They got to be like right here. Man, that person. Well, clearly there's an issue with that. There has not been a human that has been 10 foot tall. Ooh. So why would you do that? I mean, it's just a fun factoid. But it's something that we like to call extrapolation. Now, extrapolation is a double-edged sword. Extrapolation is a double-edged sword. Well, why is that? Well, clearly, I'm not a billionaire with cassette sales. Extrapolation. Extrapolation is using a prediction model for X values outside of the observed, if I can spell observed, of the observed data points. Extrapolation is using a prediction model, your line of best fit, for X values that are observed or that are outside of the observed data points. Using it for a shoe size for someone who's 10 feet tall, figuring out how much money I'm going to make from cassette tapes in the year 2000. Somehow records made a comeback. Why did that happen? Records. Don't people buy more records nowadays? I think, don't they? Aren't they mainly hipsters? What? Okay. I'm just going to say, I'm going to stand by my point. No, I'm sorry. Go ahead. I'm sorry. Go ahead. The aesthetics? Someone once told me that you do get a crisper sound out of it. Is that fair? Okay. I don't know. I don't own a record player. The last CD I bought was probably like 15 years ago. No. It was 10 years ago. It was in Walmart with that lady. No, that's a story for another day. That's a story for another day. Remind me to tell you that story one day. It happened to me at Walmart. I don't want to talk about it. Anyway. I put a star there. You know how I feel about stars in my notes. I don't put them that often. Should not put total faith in. You should not put your total faith in extrapolation. You should not put your total faith in extrapolation. Now, people extrapolate data all the stinking time. They do. People extrapolate data because they want to know, well, okay, how much money are we going to need in the next couple of years? How many people are going to live in a town in the future? My kid is this tall at this age, and clearly they're going to be growing for a little bit. How tall are they going to be at this age? I need to plan out what clothes am I going to get. Like, I can't buy my kid Christmas clothes in July when this kid is going to have a growth spurt in September. Extrapolation can be helpful. Extrapolation can help people plan for the future, but you should not put your total faith in it. You should take the results of extrapolation with a grain of salt. Some people say, don't trust it. But again, I'm telling you, there has to be a little faith in extrapolation, depending on how they do it. I'm just saying, don't put your total faith in extrapolation. Just don't believe in it wholeheartedly. Because clearly, again, cassette tapes, whatever, CDs. Anywho, 8:20 is rolling up. I'm going to say, I'm not going to assign anything today. I am going to, at some point this week, ask you to read something, but I will assign that through Google Classroom when the time is appropriate. Otherwise, I will see you all on Wednesday. So I'm going to sign off here. Click, click, and click. Storks do not bring babies. Now I got